let's get right into earthworms here, how they'll magnify the effects of climate change. So there's over 4,000 species of earthworms in the world. They take various forms. You see the giant blue earthworm here of Sri Lanka, which can be 40 inches long, and the Gippsland earthworm of Australia that can be 6 feet, which is officially the biggest earthworm in the world. These are not the ones that are invading Wisconsin and Minnesota, but it's interesting to show the diversity of earthworms. And I wasn't the first one to notice they were important. Darwin wrote a book about earthworms in 1881, and essentially in Victorian English, what this says is earthworms run the world. They really have played a huge role in how the earth got to be the way it is today. Billions of them are churning the soil all over the planet at any given time, and their cumulative impacts are absolutely gigantic, probably even bigger than the glacial cycles that we've had. So this is global warming. You've all heard of global warming, right? So this is global warming, and there's a list of 17 taxonomic families of earthworms there that you probably can't read, but it's okay. They're unpronounceable names anyway. 17 different families of earthworms, and on each continent it has some numbers. The blue ones are the families that are native to that continent. The light red ones are families that have some native and some exotic species, and the dark red ones are families that are totally exotic or non-native on a given continent. So they're on all continents except Antarctica. Earthworms are being moved all over the planet, and as an invasive species group, they really are worldwide and are probably the biggest group of invasive species with the biggest impact on ecosystems out there. I mean, the impacts of something like emerald ash borer are trivial compared to the impacts of invasive earthworms, as we'll see in a few more slides here. So this is our trophic pyramid, just to give you an idea of where earthworms fit in. We all know plants are the primary producers. They take sunlight and combine it with carbon dioxide from the air, and they make leaves, wood, and things like that. That's the food for herbivores, and then they're the food for carnivores and so on. Well, what the earthworms do is essentially take the dead leaves and recycle them much faster than they would be recycled otherwise. So that big blue arrow you see and the gray arrow, primary producers to decomposer and returning the nutrients back to the plants, they just press the gas pedal and make that process happen faster. You might think that's great. Processes go faster. Well, I'll show you what the consequences are. So they change, as invasive species, they're engineers. They change the structure of the soil, water and nutrient availability. They are a new filter on which native plant species can be successful. They affect tree growth. They affect wildlife habitat. Through ecological cascades, they affect everything. They move around as fishing bait. These days, that's how they're getting around the Midwest, because we have so many lakes and rivers and so many people who go fishing here. They originally came from Europe in the ballast of ships and in potted plants, hundreds of millions of which have been sent to the United States from Europe. And as we'll see, they facilitate other invasive species. They kind of open the ecosystem to other invasive species. These are stages of invasion, worm-free in the upper left, and you have duff or leaf litter that could be as thick as a mattress. You can walk around on it. It's nice and bouncy. It represents decades worth of leaf litter accumulation with older leaves that have turned into humus and fragmented leaves underneath the fresh leaves on the surface. When I first came to Door County as a child, almost all the forests had this type of a forest floor in Door County, with the thick, 6 inches thick like a mattress of leaf litter. And the leaves are packed down by the snow. They're kind of glued together the same way sheets of paper in a notepad that was accidentally soaked in water are stuck together. And fungal hyphae are threads that literally knit them together, so it's kind of like a thick carpet. And then the worms start to invade. You have stage 2 and 3. where there's certain species of earthworms present that kind of break up the forest floor, and then finally when you get down to stage 5, which is dominated by night crawlers, Lumbricus terrestris, then there is no leaf litter and you can have bare mineral soil on the forest floor. How do I know all this? Well, these are the people who did all the work. If you want to study earthworms, you have to have really good knees because you're going to kneel all day or you're going to bend over all day to be down on the ground to sample earthworms. So Cindy Hale was my first PhD student to study worms there. Andy Holsworth in the lower right also got his PhD studying earthworms. He now works at the DNR of Minnesota as a policy analyst. And Dave Chafin in the top right did a project to look at earthworm invasion in wilderness areas, including the boundary waters, and found worms throughout the most remote wilderness in the eastern half of the United States. He was just hired by the Nature Conservancy to be director of their worldwide boreal forest conservation program. And he hasn't finished his PhD yet. You can tell the economy is better because students are getting jobs before they finish their degree. So here's how they got here. They came on ships to North America. They went to settlements where European settlers went, so cities first, and then to rural areas by live fishing bait, and then which you can buy out of vending machines in northern Wisconsin. You can buy live worms from a vending machine. And then they spread from the lake shores until they reach an ATV trail, and then they travel around on the tires in the mud. At least the eggs of the earthworms can do that. So they get across the landscape pretty efficiently, being transported by people. How do we know about the earthworm impacts? Well, they have leading edges of invasion. Usually these originate at fishing docks or campsites, and they move slowly through the woods, and so we can compare in front and behind the leading edge of invasion, which is portrayed as the blue line here. And here's how to sample them. We use ground yellow mustard powder mixed with water in a milk jug, as you see. Pour it on the ground in a small area, a little bigger than a square foot. About half of it, wait for some worms to come to the surface, then the other half, it irritates their skin slightly, and that makes them come to the surface. Then you pick them up, put them in a Tupperware container, and takes about 15 minutes sometimes for the slowest worms that are deeper in the soil for that mustard to get through. They'll also respond to electricity. We have used electrodes inserted in the soil to bring them to the surface as well. And here are some of our players. You probably all know the nightcrawler, the biggest one. Typically 6 inches long. I've seen them 8 or 10 inches long. And it is a finicky worm. It only eats fresh leaf litter, the leaves that just fell the previous fall. And its relative Lumbricus rubellus there in the lower left, called the leafworm, it's not finicky. It'll eat the old leaves that are 50 years old and the humus and the older things. They're the ones that destroy the forest floor when the invasion comes, and then the nightcrawler moves in and eats all the new leaves that fall, essentially making this leaf-free state of the forest floor permanent. In the lower right, you have what is commonly called the angleworm. There are actually 6 or 7 species. They don't have as much pigment in their skin. You can hold them up to the light and see soil particles moving through their intestinal system. They spend all their time in the soil. They're what we call endogeic. They only come to the surface once or twice a year, which they do in a big mass, usually in April, the first warm, rainy night of the season. And this is what they do to soil. So on top is a forest floor, a core of it from an almost earthworm-free site. And everything you see there from the black going over towards the right, that's all leaf litter in different stages of decay. The black humus, then the fragmented leaves, and then bigger chunks of leaves, and finally fresh litter on top. And then in the middle and late stages, that organic layer of leaves on the surface gets thinner and thinner. Obviously, right after the leaves fall in October, it can still be maybe a ½ inch thick, but by the middle of the following summer. It'll be gone. The soil profile turns into a black A horizon, which is pretty much identical to the type of horizon you get in a plowed field, plowed by a farmer. In this case, it's just millions of worms doing the plowing. And here's one spot at one of our study sites in northern Minnesota. And on the left, everything from the black layer all the way to the top, it's 6 inches thick. It's like a big spongy mattress. That's all organic matter. Same spot 10 years later, and instead of 6 inches of organic matter, there's about a ½ inch on the top of the soil. And the mineral soil underneath is already starting to be stained black because the earthworms convert the carbon into black carbon that then turns the A horizon black. So here's a Lumbricus terrestris out looking for its dinner. And they don't call them night crawlers for nothing. If you go out in late April or early May, the first warm night when it's rainy and the leaves are wet, you will hear the leaves rustling throughout the forest. And you have to go out at like 10 or 11 at night. And it is noisy out there. They are moving through the leaf litter that fell the previous October, searching for the leaves they want to eat. And believe it or not, they sort the leaves by species of tree. On the lower left is an experiment we did with 1/3 basswood leaves, 1/3 sugar maple, and 1/3 red oak. And we put those mixtures on the ground in the forest and then observed what the earthworms did. And in this one, the pen is pointing to the entrance to a nightcrawler burrow. And all of the leaves next to the burrow are basswood leaves. So this worm went out, looked all around, found basswood leaves, and dragged those back to its burrow to eat. If you look at the same place in August, now, same burrow, same earthworm, the basswood leaves have been eaten, the sugar maple leaves have been eaten, and now they've pulled the oak leaves over next to their burrow. It's their least preferred leaf, but if everything else is gone, they'll eat it. And you can see the petioles of the other leaves, the stems, which they don't eat, are just laying on the soil surface there. This particular worm has 2 entrances to its burrow. A lot of them do. They start like that and they come together about a foot below and then continue as a single burrow going down about 6 feet if the soil is that deep. It's just their back door. In case one gets clogged up, they can go out the other entrance. So they can sort leaves, and it turns out it's according to the calcium content of the leaves. Basswood leaves have more calcium. Maple leaves are second, oak leaves are third. And what they do with the calcium is they store it up in their bodies. And if you get a rainy period where it rains every day for 2 weeks and there's no oxygen in the soil, they combine that calcium with carbon dioxide in their blood. That makes calcium carbonate and they excrete it. It's a very inefficient way to breathe. Don't try it. They almost tried it on Apollo 13, remember? When their air filtration system broke and the engineers in Houston had to tell them how to build a CO2 filter out of only what was present on the space capsule, and they were successful in doing that, and the astronauts survived, but earthworms figured out how to do that 300 million years ago. So people aren't as smart as they think. So here's what they do to the soil. They change the bulk density, which is how hard the soil is. Obviously, they eat that organic layer or leaf litter layer off the top. They compact the soil. A lot of people don't understand that because native forest soils have all sorts of species like centipedes and beetles and small mammals and salamanders, and they make all sorts of tunnels in the soil that are permanently maintained. So the soil's like a sponge. And when the worms come, they displace all of that, and those tunnels all collapse, and they actually increase the density of the soil. That makes water run off during heavy rain events, less soaks in, so it makes the forest more droughty. So it alters the food web in the soil and all the microbial processes that regulate nutrient flow. Nitrogen, phosphorus, potassium, calcium, and magnesium, which are really important nutrients, are leached out of the soil. Potassium in particular is leached out and goes into the water where it causes algal blooms. This alters the habitat in all sorts of ways for every different species of plant, changes the whole plant community, and when you change the plant community, you change the wildlife species that can live there. All wildlife species depend on plants. They either eat plants or they live in plants as a habitat, or they eat another animal species that does eat plants. So these are the effects. Then if you take those basic effects and follow them through, it creates things that are of concern to humans, like disease dynamics. They influence the abundance of mice on the forest floor that carry Lyme disease, for example. The voles become less abundant in mice. More abundant in the mice are the carriers of Lyme disease. They affect many different types of diseases by changing the soil. They facilitate invasive species. As I mentioned, change plant community composition and initiate concerns for the conservation of native species. They affect forest and crop productivity. In Minnesota, they reduce the productivity of soybeans, for example. And I'll let you puzzle over that, and if you really want to know, you can ask during the questions. They reduce forest productivity, and I'll show that in just a minute. They reduce soil and water quality. They affect climate change and carbon dioxide emissions from the soil, which is one of the big points for this lecture. And they even affect the ability of windstorms to blow down trees. I'll let you puzzle over that too. They affect the fire regime because without the contiguous leaf litter on the forest floor, it's hard to get a prescribed fire these days to run through the forest, which is making it really hard to regenerate oak in places like southern Wisconsin and southern Minnesota. There's a fair amount of red oak in Door County, and without fires, that is not going to reproduce very well. So, but you can't run a prescribed fire through these forests very easily without that contiguous leaf litter. So this is just a graph that shows nitrogen and phosphorus. It's NH4 is ammonium, NO3 is nitrate, PO4 is phosphate. I'm sure you all knew that, but without worms is the black bar and with worms is the gray bar. So a lot of these nutrients do leach out of the soil, and so there's a lot less nutrient availability in the soil when the earthworms invade, and they increase the density of the soil. This is one of our transect sites. It's at Leech Lake in northern Minnesota. It's a sugar maple forest, not all that different from a lot of the forests in Door County. And you don't even need to read the paper because the whole results are in the title. Invasive earthworms deplete key soil inorganic nutrients. These are all things that are tremendously important to the growth of sugar maple. And I'll show you the impacts to sugar maple in just a minute. All right, well, right here. You've seen maples around Door County with dead branches up high in the crown like this, right? Some of those are next to highways, and that's because of all the salt. Others are in the middle of the forest, and you still see that, and it's not because of salt, it's because the earthworms invaded. They stripped off the leaf litter. It no longer insulates the soil and keeps it cool during the summer. So the fine root system experiences drought, and then with the lack of phosphorus and nitrogen and calcium that the earthworms cause, the trees have reduced growth and some of the branches die. The graph that you see there, it's growth rate of sugar maples from 120 different forests all across northern Wisconsin, upper Michigan, and northern Minnesota from 1950 up to about 2012. The thick black line is the growth rate of sugar maples averaged over all those plots on plots that were heavily infested with earthworms. The other lines up above are the growth rates of sugar maples on sites without heavy earthworm impacts. It's about a 30% reduction in the growth rate of sugar maples. Negatively impacts their ability to produce syrup and ability to produce seeds. There are fewer seedlings on the forest floor. Seeds demand a lot of nutrients that they no longer have after the worms invade. Here's the base of a sugar maple pre-earthworm invasion. And if you look carefully here, you can see about 11 species of native plants. Right? There's a couple species of ferns there. There's sugar maple seedlings, there's twisted stalk, Solomon seal, yellow violets. There's some seedlings of sweet Sicily in there. There's Carex pennsylvanica, which is that grass-like plant or sedge. Here is post-earthworm invasion. We call this forest gingivitis. Gingivitis is when your gums recede and your roots at your teeth show. Well, the forest floor recedes when earthworms invade and the roots show, and maple trees, or no tree is happy about having its root system exposed like this. So look at how far the forest floor sank, and look at the diversity of native plants in this picture. Not very high compared to what it was. And this picture was taken in May, and look at all the leaves. They're standing up. After being under 2 feet of snow all winter, they're standing up. Why are they doing that? Because every one of them is being pulled into a burrow by an earthworm. So the impacts on plants of all these changes, they're winners and losers. Sedges are winners. They're grass-like plants that form like a lawn. Jack in the pulpit does really well. There's a whole suite of native plants that do well. The losers are things like trilliums, violets, orchids, twisted stalk, sweet Sicily. They're all the losers in this. Here's an example, one of the rattlesnake plantain orchids. It requires a fungus to germinate, to be a symbiotic partner in the germination process, because the seeds are so small they don't have their own food. They depend on the fungus. Well, those fungi live in that leaf litter that disappears. In addition, orchid seeds are small. A lot of them go inside the worm and they're either digested, or if they're cast out, they could be cast out 6 inches below the surface where they just can't grow. And Botrychium mormo is a small plant that is known to disappear when Lumbricus rubellus, the leafworm, invades a given site. So it disappeared on 28 sites in the Chippewa National Forest when this particular worm species invaded. So here's the whole syndrome. I call it forest decline syndrome. You introduce the worms, the duff or the leaf litter goes away. That makes the soil warmer and drier. All the plants and tree seedlings that were rooted in that duff are killed. Their rooting medium is literally eaten out from under them, so that the standing crop of adult plants of things like trilliums can die. You still have the same number of deer, fewer plants, so the deer to plant ratio is higher. The deer can finish off the rest of the plants. That leads to an increase in Pennsylvania sedge, because deer don't like pen sedge and neither do worms. If you've ever run your finger the wrong way along the edge of a sedge, they have all those little sharp teeth, and if you run your fingers up, it will slice right into your skin. Well, that's why neither deer nor worms like to eat them. And they then become abundant. So the nutrients leach away, and then you get the forest dieback and regeneration failure, and your lush community of many species of herbs is replaced by a simple one or invasive species. These also affect the transition from boreal to temperate forest, which we expect in a warming climate, right? The spruce and fir that we have on the east coast of the peninsula here. As the climate warms, it might become temperate forest, which would be maple and basswood and oak. The worms might accelerate that process because they create a good seed bed for things like red maple and oak. And so they'll have a big influence on that process in other ways that I'll show in a few minutes. So here's our sugar maple forests of the historic or of the past. In the upper left, that shows white snakeroot in August. In the spring, it would be trilliums. And in the future, it'll be more oak infiltrating those forests, more red maple than sugar maple. Red maple is heavily favored in earthworm-invaded areas, and a carpet of sedge rather than many, many species of plants. And that affects wildlife. You may know the ovenbird. It's a songbird that lives on the forest floor, builds its nest on the forest floor. If you were an ovenbird, which of these two habitats would you pick? The upper one or the lower one? Knowing that hawks and owls are in the canopy looking down, they don't want to build their nest on those bare earthworm invaded sites. And in fact, the more earthworm biomass there is, according to the study one of our PhD students did, the fewer ovenbirds there are. So here's a sedge lawn in Peninsula State Park. This is late stage earthworm invasion. Very common in Peninsula. I haven't found any sites without worms there yet, but maybe I have to hike deeper into the park. Very heavily invaded and not very diverse in terms of the species. And here's an invasion front, a more recent invasion front. The sedges haven't had time to take over yet near campsite number 7 in Newport State Park. And here you see the worms, the night crawlers, have gathered all the leaves into little bunches. And there's bare soil appearing. I think this was in, actually this was in late June. So even by late June, they had eaten almost all the leaves that fell the year before. So these invasions are pretty common in Door County right now. I was driving yesterday through the middle of the peninsula and noticed that most of the sugar maple forest looked like this with the sedge lawn. So that's a major transition since I was a young kid when our family first started coming to Door County. We didn't have any sedge lawns in Door County then, and we have lots of them now. Then they also allow things like buckthorn to invade. Now there's only buckthorn, as far as I know, in the far, far southern part of Door County, and you should keep it there. It's here? Oh, okay. Well, organize some parties and go out and get rid of it, because as the earthworms spread through the county, the whole county will become buckthorn, because buckthorn loves earthworm invaded sites. Buckthorn and earthworms co-evolved with each other on their home continent. Nothing could make both of them happier than to have the other partner show up. So not only buckthorn, but garlic mustard is essentially restricted to earthworm invaded sites, and Tartarian honeysuckle and many other invasive plant species. So here's a study we did of interactions between global warming and global worming. And we took a bunch of seeds of native plant species and plant species from Europe. I think we had 6 or 7 species of each. And we grew them in little pots in growth chambers in the basement of the building where I work, which you can program for any climate. So we programmed them for the climate of Cloquet, Minnesota, and so they give you the average nightly low and the average daily high, the same progression of light throughout the day that you would get at Cloquet, Minnesota. And then we did Cloquet plus 4 degrees Celsius or 7 degrees Fahrenheit in order to simulate a future warmer climate. And we had earthworms in some of the pots and not in others. And this is a non-metric multidimensional scaling graph, which you don't have to know anything about. So let me tell you what it said. What it essentially says is 4 degrees Celsius of temperature difference compared to the control only made a difference in the community composition as long as that red line. Whereas having 3 species of earthworms compared to the control of no earthworms made as much difference in species composition as that longer brown line. So 3 times as much difference in the composition of the little plant communities that emerged were caused by worms as by 4 degrees Celsius of warming. And global warming and global warming are going to occur at the same time, so you can see this is going to lead to very, very big changes in plant communities, which will then follow on into wildlife species. Oh, and the worms dried the soil surface more than the warming temperatures. And that's because they drill their little burrows and the water drains away from the surface to the subsoil. And in that surface layer, it's very, very dry, and that makes it really difficult for newly germinating plants to become established. What about their impact on carbon dioxide? So forest floors are made of carbon, all that leaf litter they're eating. Well, these 2 papers were published at about the same time. One One of them says, earthworms facilitate carbon sequestration, essentially, and there's a bunch of gobbledygook language there you don't need to know. Essentially, the paper on the top says they make more carbon be stored in the soil, and the paper on the bottom that was published say they cause carbon dioxide to be emitted from the soil. And it appears that these two papers are in conflict with each other, but if you dig a little deeper, they aren't. I happen to be the peer reviewer for both of these papers, and they're in different journals, so I was the only one who knew these two papers with apparently diametrically opposed views were being published. Well, it turns out that they're both right. When the worms first invade and they eat the forest floor, they are turning all of that into carbon dioxide. And they're invading vast millions and millions of acres all across Canada, from Alberta all the way to Quebec, the whole northern tier of the United States now, eating those forest floors and turning millions of tons of forest floor into carbon dioxide. Later on, as the decades pass, they will re-sequester carbon into their burrows, but that's a slow process. It'll take decades to centuries for the worms to put the carbon back in the soil that they had initially emitted when they first invaded. This is what a forest floor on the left looks like. That's from northern Minnesota, from a sugar maple forest. And again, this is almost pure organic matter. Even the black on the bottom is humus. And we did an experiment in pots just to see how fast the forest floor decomposed. Well, we put these round plugs of forest floor that were earthworm free, put the worms in, and 3 weeks later we had the picture on the right, and the bubbly things are earthworm castings, and you can see no more forest floor there. The brown stem that goes across the picture, that's a sugar maple seedling that was growing there. It was being held up by the forest floor. It tipped over, and you can see its fine root system all exposed to the air there as the worms ate that organic matter. So the earthworms eat forest floors, emit huge amounts of carbon dioxide, and then very gradually, by having enriched castings that are enriched in carbon over probably a few centuries, they will store a lot of carbon in the soil. But their timing is really bad because they're emitting huge amounts of carbon dioxide right now. In the next few decades are really critical for the future of the planet in terms of the amount of carbon dioxide in the atmosphere. And the worms are not going to put the carbon back into the soil fast enough to help us at this point. So back to this that I showed you earlier. So we've talked about plant communities facilitating invasive species, soil and water, forest productivity. I just talked about CO2. So let me put earthworms in the scheme of things here. This shows all the negative influences on trees in the Midwest at this time. In the blue ovals, one is more frequent and longer droughts. Well, earthworms make droughts worse at the same time as droughts are becoming longer because of climate change. More deer, well, I already told you that deer interact with earthworms is kind of a double whammy on native plants. And climate change is another, it's a triple whammy then. More fires and more windstorms are happening. Well, I told you earthworms might counteract that a little bit by reducing fires a little bit, and they might reduce wind throw of trees a little bit. And I hope you're still puzzling over how that works. And we'll ask a question in a minute because I'm almost done. We have all these pests and diseases of trees. All these things are acting against trees, things like emerald ash borer and Dutch elm disease, but worms are right in there with those major effects. In fact, earthworms can make a lot of them worse, and that's why they're going to magnify the effects of global warming on the forests, because they're adding to drought stress, they're adding to the stress caused by disease, they're adding to the stress caused by deer and by fire. And it's not so much the direct temperature that impacts forests and climate change, it's these things, the droughts, the fires, the windstorms, the deer, the invasive species. Climate change changes those, and those change the forest. And so that's why earthworms are so important here. They have their direct impacts, and they interact with a lot of the other changes that are happening in a changing climate. So, earthworm invasion will magnify climate warming by emitting CO2 to the atmosphere, a direct effect, exacerbating drought effects, accelerating conversions of boreal forest to temperate forest, increasing biodiversity losses. I mean, the real reason scientists are concerned about global warming isn't because you'll have to turn up your air conditioner a little bit in summer, it's that it will accelerate the loss of biodiversity on the planet. And that's an irretrievable loss. The recovery time there is tens of millions of years. Earthworms accelerate biodiversity loss in areas where they invade, and then they're facilitating invasive species that are better at growing in a changing climate than the native species are, because invasive plant species by nature just have a wide tolerance, and they're occupying places where native plants could grow in an environment that's getting increasingly hostile to native plants. So that's how they magnify the impacts. Thank you.